Alright, welcome folks. This will be lecture 16 in our probability and statistics course, the first part of the lecture. This lecture is meant to cover our meeting for Friday, April 3rd. I will start including the dates in all of these lectures so that you can piece together more easily what happens when and keep track of all these things as we're doing them asynchronously. This is our lecture for Friday, April 3rd. So we last time talked about continuous random variables for the first time. In particular, we talked about the probability density function and the cumulative distribution function associated with a continuous random variable. All random variables amount to a collection of values which are possible, and some means of characterizing the likelihood with which those values occur. For discrete random variables, we had a sample space and a probability mass function. For continuous random variables, we have a sample space and a probability density function. One of the key points when you're talking about continuous random variables is that you calculate probabilities by integrating the density function. Just like for discrete random variables, we calculated probabilities by adding up values of the probability mass function. We will see some more explicit examples of this work today. We've been front-loading some theoretical stuff here, but we will get our hands dirty with some examples today and see a more overt illustration of how the density function gives us likelihoods. So today we are going to talk about expected value, variance, and or standard deviation. So variance and standard deviation are basically the same idea, but expected value and variance, or expected value and standard deviation if you like, are the two primary properties that one would be interested in. Once you've got the definition locked down, those are the next two most natural factors or properties of a random variable to ask about. Expected value and variance were both defined for us for discrete random variables in terms of sums. And as we move from the realm of discrete random variables to the realm of continuous random variables, those sums are going to turn into integrals. As I've said before, integrals are the continuous version of sums. In fact, that's why the integral symbol looks like an elongated S. So let's begin with the definition for the expected value of a continuous random variable. If you've got a continuous random variable and you have its PDF, you can define the expected value, also called the mean, of that random variable. And we're using the same symbols here as we did for discrete random variables, the fancy E and the Greek letter mu. And it is defined to be x times the density function for big X taken at little x, and integrate that product across the whole real line. So when I do an integral with the subscript of r here, if you haven't seen that before, I just mean the integral from negative infinity to positive infinity. It's a nice shorthand for that statement. So this is the definition of expected value when this integral exists. There do exist random variables in the world for which this integral is not convergent, we would say, where you actually get an infinite value for this integral. But we are not going to concern ourselves with such in this course. I'd be happy to talk to you about them in office hours. Cauchy's random variable is one, if you'd like to look that up. But the random variables that will be of interest to us have a finite expected value. So the intuition for expected value for continuous random variables is going to be the same as it was for discrete random variables. We're still talking about possible values, here little x, each of them being weighted by their associated likelihood, where that's now given by the PDF instead of the density function. So it's still taking all the values that are possible, weighting them each by how likely they are to actually occur, and then integrating that product to create a probabilistic average, where the more likely values will contribute more heavily to the probabilistic average, and the less likely values will not contribute as much. So we have exactly the same interpretation for expected value here as we did for discrete random variables. In fact, we can lay out the formula for the expected value for a discrete random variable and the expected value for a continuous random variable, and you can see how closely these two concepts are tied. Turn the Greek capital sigma into this elongated S, and you basically have the same formula here. In both cases, it's a value that's possible, and that gets weighted by the likelihood of that value occurring. We will define the variance of a continuous random variable. This is going to look even more similar to the case of discrete random variables than expected value did. So if you've got a continuous random variable, you've got its PDF, we define the variance. Again, we use the same symbols, var and sigma squared. and it is again going to be the expected value of the square of the difference between the random variable and its mean, defined on the previous slide. And intuition is again the same. Variance is the expected squared distance from the mean, just as it was from discrete random variables. Big picture, even more basic, variance still gives you some sense of how much spread do you expect in the values associated with this random variable. So if all the values that are reasonably likely for the random variable are clustered tightly about the mean for that random variable, then it is a low variance random variable. It does not vary much. It is low variance. If it is a high variance random variable, then you are not at all surprised to see the values that are observed actually differ in a significant way from the mean. You expect large square distances from the mean for high variance random variables. We talked about darts. My buddy Miles is good. His throws are low variance. I am not so good. Sometimes I hit the wall. Mine are high variance. Looking at the formulas for discrete and continuous random variables, the formulas for variance for the cases of discrete and continuous random variables, they look exactly the same. The difference is that expected value is defined slightly differently in these two contexts. So here this expected value is a sum, and this expected value is an integral. But even that is largely a cosmetic difference. We just saw in the previous slide that expected value works mostly the same way in the two contexts with some technical differences, and variance is defined in exactly the same way with those two different versions of expected value. So, all of our intuitions carry over. Variance for continuous random variables works intuitively just like it did for discrete random variables. More than that, we also have our formula that we had in the realm of discrete random variables for calculating variance. So as we said back then, the definition is nice because it helps you to see what the intuition should be. It gives you a greater understanding of what variance measures and how to think about it. But for computing variance, it is often preferable to make use of this formula. So the formula says that the variance of x is given by the expected value of the square minus the square of the expected value. And to make use of this definition, and actually also to make use of this theorem, and actually also to make use of the previous definition that we had, you actually need this theorem. So this theorem tells us that the expected value of some function of the random variable is going to be given by this integral. It looks a great deal like the expected value of the random variable itself, except instead of taking the possible values for the random variable, we are taking h of those possible values. Again, there is an exact analog to this theorem in the realm of discrete random variables. A ton of what we're doing is carrying over. It's just that sums have turned into integrals. So feel free to look back through those notes, and you will find a theorem that involves the sum of h of all the xi weighted by the PMF. It looks just like this, but the sum is now an integral. What this allows us to do, in particular, is to compute the expected value of big X squared, and that would be involved in this theorem here. And what I'll do to compute the expected value of big X squared is I'll integrate across the whole real line, I'll have little x squared, and I'll have that weighted by the density function associated with big X. And we'll do examples presently. And finally, we have defined expected value and we have defined variance. We can now define standard deviation. As before, standard deviation is just the square root of the variance. We're using the same symbol, sigma sub x. And the intuition is the same as well. Where variance is the expected squared distance from the mean, standard deviation is more like just the expected distance from the mean. The square root is meant to counteract the square that's involved in the definition of variance. And so this is more literally like how far away from the mean do you expect the values to be. More useful in many practical applications, why engineers prefer the concept of standard deviation, but the square root is mathematically annoying, so mathematicians tend to speak more of variance. Alright, so let's do some problems here. These problems, we are going to compute things like expected value and standard deviation, but more than that, we're going to spend some time thinking about the density function and how the graphs of the density functions relate to probabilities. We're going to spend a little bit of time developing intuition for these types of problems. And we'll have some like this on the homework that will go up Friday. I say ambitiously. This week has been brutal, but Saturday at the latest, and I'll let you know if I don't get it up on Friday. So, let us let x be a continuous random variable, and I am going to give you the definition of x in the form of the sample space and also the probability density function associated with this random variable. So if this is a continuous random variable, its sample space should be an interval of the real line, and in particular we take it to be the interval from 0 to 1. The probability density function I'm going to give you in this form. This is what's known as a piecewise definition for a function. It is likely, depending on who taught you calculus, that you saw functions of this type when you started to study the idea of continuity. So if you have your textbook for calculus still, you could refer back to the sections on continuity and discontinuity, and it's likely you saw functions of this type. We will review it a bit here today. We'll think about it, and we'll certainly draw the graph of this function. But if you are not comfortable with these functions defined in this way, I would be happy to talk more to you about that in office hours. So what we're saying here is that little f, my density function, it's going to have two different definitions for different regions of the real line. So when I take little f at little x for input point little x, if that input point is in the interval from 0 to 1, then the definition of the function is 2x. So if I feed this little f at a third, 1/3 is in the interval from 0 to 1, so I get 2 times 1/3, which would be 2/3 at that point, and so forth. If your little x is not in that interval, then your density function just has value 0. It's 0 everywhere except in the interval from 0 to 1. So we can graph this, and we will do so shortly. But first, the question asks us to find the probability that our random variable is in the interval from 0 to 1/4. Find the probability that our random variable falls in the interval from 7/8, not including 7/8 here with the soft edge, up to and including 2. So in the half open interval, one might say, from 7/8 to 2. And then they also ask us to find the expected value, and we are asked to find the standard deviation associated with this random variable. And so let's do this. And the first thing that I'm going to do is I'm going to actually draw the density function for little f. This is math. If I can draw pictures, I'm going to draw pictures. They give me a firmer footing, and they allow me to have a more concrete sense of what's going on in the problem. So I'm going to begin, I'm backing up here, I'm going to begin with this definition of the density function, and I'm going to sketch its graph. So here between 0 and 1, our density function was equal to the function 2x. So we've got this linear graph with a slope of 2 and a y-intercept of 0, which is why it's crossing through the origin here. And so this would be 0.01, I'm sorry, we're coming over here to 1, 0, and we would go up 2 units to see height 2 right at this point above 0.1. So that's what the function looks like between 0 and 1. We were also told that little f was equal to 0 everywhere else. So that's why I have darkened the x-axis. Little f equal to 0 represents the x-axis everywhere off of the interval from 0 to 1. And it's also worth noting that I'm filling in the circle here, meaning at point 1, little f takes that value 2, and little f takes value 0 for every point greater than 1, but not equal to 1. So again, if you are not comfortable with these piecewise defined functions, please try to become comfortable with them. Make some sense of this definition, come in and ask questions, or refer to any standard calculus texts and its section on discontinuity early in the material for Calculus 1. So that's what the density function looks like. That's what the PDF looks like. The idea of the PDF is that if I take any interval in here, mostly we'll be thinking about intervals that lie within 0 and 1. So if I draw a little left-hand endpoint right here, and I come over here and I draw a little right-hand endpoint, and I want the likelihood that my random variable falls in that little subinterval, that likelihood is given by the integral of the density function across that subinterval. So the random variable is going to live down here on the horizontal axis. The density function, which comes up in the vertical axis, is telling us how likely is it that the random variable shows up in different regions. So over here on the right-hand side, where the density function is so tall, if I drew a little interval that goes maybe from, say, 3/4 up to 1, there's a fair amount of area under the curve here, between 3/4 and 1, meaning that it's fairly likely that my random variable shows up in that interval. If I draw a symmetric interval over here on the left, say from 0 to 1/4, and we're actually going to talk about that one explicitly, there's less area involved under the curve above that interval. And that means that it is less likely that the random variable shows up in that interval. The likelihood that the random variable shows up in an interval is given by the integral of the density function, which is to say the area under the curve for the density function associated with that interval. So that's the big picture stuff. Density functions, you integrate them, which is to say you find the area under them, and they give you the associated likelihood for your random variables showing up in different regions of the horizontal axis here. So let's compute one of these explicitly. Part A, we want the probability that x shows up between 0 and 4. Well, it's actually stated as the probability that x lands in the interval from 0 to 4. I can rewrite that as the probability that 0 is less than or equal to x, which is less than or equal to 4. That probability is given by the integral of the density function from 0 to 1/4. Now, the density function has different definitions in different regions of the line. It's doing one thing over here on the left, it's 0. It's doing a different thing here between 0 and 1. And it's doing really the first thing again. It's being 0 again once we get past 1. You might say that there's 3 regions, less than 0, between 0 and 1, and greater than 1, where the density function has different behaviors. Sometimes the interval that you're interested in, as we will see when we consider part B, actually straddles one of these division points, and you have to break up your integrals into 2 pieces. But this interval, 0 to 1/4, lies entirely inside one of these subregions where little f is going to have consistent behavior across the whole of that subregion. So we're able to compute this integral straight away. Between 0 and 1/4, little f is just 2x. So we're looking at the integral of 2x between 0 and 1/4, and this is one of the easiest problems you might see in Calc 2. It's just a polynomial integral with simple limits of integration. Everything is nice and dandy. The antiderivative of 2x is x squared. We're going from 0 to 1/4. We plug in the 2 limits of integration, take the difference, and we're getting 1 over 16 minus 0, which is 1 over 16. So that is that probability. There's a 1 in 16 chance of the random variable actually showing up in that interval. And again, what we're doing here is, ignore this dot, that was a typo. What we're doing here is we're looking at this density function. We're taking the integral from 0 to 1/4, and we're finding the area under the density curve above that interval. That area, which is to say the integral of the density function, is the likelihood of our random variable showing up in that region. So I want to know, how likely is it my random variable is going to show up somewhere between 0 and 1. How likely is it that it shows up between 0 and 1/4? I find that value by finding the integral of the density function, or the area under the density curve here between 0 and 1/4. Now let's do another one. So the probability that we show up, that our random variable shows up between 7/8 and 2. And I'm going to go ahead and ignore the fact that I would normally write this as 7/8 being strictly less than x, which would then be less than or equal to 2, based on having the soft bracket here, which excludes the left endpoint, and the hard bracket here, which includes the right endpoint. Because as we talked about last time, it doesn't matter whether you use strict or non-strict inequalities for continuous random variables, because the likelihood that a continuous random variable ever falls at an endpoint is always 0. I'm free to go ahead and toss out that information, the fact that this was the soft bracket and we excluded 7/8, and go ahead and include less than or equal to symbols in both of these positions. So the probability that x falls in this interval is just the probability that x ends up between those two numbers. By the definition of the density function, that's going to be the integral of the density function across that interval. Now there's a bit of an issue, because the density function is doing one thing between 7/8 and 1. Between 7/8, which is somewhere over here, and 1, my density function has got this 2x formula that defines it. Whereas between 1 and 2 out here, it has the value 0 everywhere. So my density function doesn't behave consistently over the whole of this interval, and I actually have to break this interval up into pieces where the density function does behave consistently. So instead of going from 7/8 to 2 in one shot, I've got to think about what's happening between 7/8 and 1, and that's one piece of the density function, and then also what's happening between 1 and 2. So the points where your density function changes its definition, you may have to break your integrals up so that each little subintegral fits entirely inside a region where your density function has a consistent definition. So here I'm taking 7/8 to 1 because between 7/8 and 1 my density function is 2x everywhere, and between 1 and 2 my density function is equal to 0 throughout. So the points where little f changes definition are going to give you natural breakpoints in any integrals that you must compute. If those breakpoints occur inside of an integral, you're going to have to break up your integral and use those breakpoints as new internal limits of integration. This is legal. This is something that was talked about in Calc 2. We actually discussed this a bit when we were talking about one of the theorems in the last lecture, where we could think about probabilities in terms of the differences of the values of big F. And we reminded ourselves that you can take this integral. If I wanted the whole of this triangle, for instance, in that area, I could find the area to the left of 1/2, the integral from 0 to 1/2, and I could find the area to the right of 1/2, the integral from 1/2 to 1. And the sum of those two areas would give me the whole of the area of the triangle. So integrals play nice in that way. You're able to break them up according to internal division points, as we're doing here. And this allows me to say that between 7/8 and 1, my density function is always 2, whereas between 1 and 2, my density function has value 0. Integrating 0 from 1 to 2 is just going to give me 0. I'm left with the integral of 2x. That antiderivative is x squared. I've got new limits of integration now, and I'm going to get 1 minus, this is 7 squared over 8 squared here, and with a common denominator it comes out to be 15 over 64. So let's draw another picture. Here we had the integral from 0 to 1, which is where our random variable, or our density function rather, is doing something interesting, and then the density function is 0 to the right of 1. We had an interval here, which I've dropped some square brackets on the horizontal axis to indicate the interval. We were interested in the probability that our random variable showed up between those square brackets. But actually, for this random variable, there was a 0 chance that it showed up between 1 and 2. So the probability that it showed up between 7/8 and 2 was just the same as the probability that it showed up between 7/8 and 1. And the probability that it showed up between 7/8 and 1 is given by the area under the density curve between 7/8 and 1, which is to say the integral of the density curve from 7/8 to 1. And we found that area to be a 15 over 64. Again, forgive my typos. That is a 15 now that I have written over the 6. And as we just said, that's the probability of the random variable showing up between 7/8 and 1, which is the same as the probability of the random variable showing up between 7/8 and 2. And this is the probability we were originally asked for. This equals this because there's 0 chance it shows up between 1 and 2. And this equals that because we integrated the density function for this random variable across that interval, and we found that to be the value. So now we've been asked to find the expected value of this random variable. We're just going to write down the definition and we are going to see if we can process it. So the expected value of any random variable is the integral across the whole real line of x times the density function at x dx. This is our definition of expected value. We've got possible values weighted by their likelihood, and we're integrating all of those weighted possible values together to get our probabilistic average. This is where I did something stupid and scribbled over it rather than rewrite the slide. And now to integrate across the whole of the real line, as we said before, the density function is doing one thing to the left of 0, is doing something else between 0 and 1, and then it goes back to doing the first thing once you get past 1. So we're actually going to have to break this integral over the whole real line up into 3 integrals that correspond to the 3 different sort of domains of consistency for little f, if we wanted to make up a phrase. The 3 chunks of the real line, either finite or half-infinite intervals, where f has consistent behavior, little f. So we're going to break up this integral over all of r to the integral from negative infinity up to 0, from 0 to 1, and then from 1 to infinity. And between negative infinity and 0, little f is just 0. Between 1 and infinity, little f is just 0. But between 0 and 1, little f is equal to 2x. So these two outer integrals drop off, and I'm just going to be left with this integral between 0 and 1 of x times the density function, which in that region is equal to 2x. If you were doing a problem of this type, so if I give you a random variable and I ask for the expected value, I'm not going to require you to write out these 0 integrals. I'm being very explicit here because I want to make it clear to folks what's happening. But if you jumped from saying the expected value of x equals this is the definition, and you jumped straight into writing that being equal to the integral from 0 to 1 of this integrand, I would be more than happy with that. That would certainly be a full credit answer. But this is what's going on. So now we got to compute this, and again, it's relatively trivial. 0 to 1, 2x squared. We're going to get a 2 over 3 x cubed. From 0 to 1, we plug in the limits of integration, we get 2/3. I say it's trivial because it's one of the simpler integrals from Calc 2. I also should say that I recognize that it's been a while since some folks took Calc 2, and maybe even when you took it, you didn't get the handle on it that you would have liked. So I don't mean to dissuade you from coming to ask me about these problems if you have questions. This is definitely foundational stuff, and we do want to make sure that everybody's got a handle on it. So feel free to let me know if you're having difficulty with any of the calculus that we're doing here. But we're getting 2/3 for our expected value. And so here again is my density function. Here's sort of the midway point, not sort of, the midway point between 0 and 1, 1/2. And we're finding that the expected value is over here at the 2/3 mark. So it's pulling a little bit to the right here. And the reason for that is because the values on the right half of the line are the more likely values to actually occur. So they are weighing into that average more heavily. Still, if over here near 0, it's not real likely to occur, as evidenced by the low density function, the small values for the density function over here. So these values are going to be less likely to actually happen, and therefore they contribute less to the probabilistic average that we call expected value. Another way to think about this, I've stated the same thing here, is the probability that x shows up on the left half of this interval is going to be smaller than the probability that x shows up on the right half. That's illustrated here with these pictures. The area under the curve on the left half of the density function between 0 and 1 is going to be a smaller area than the area on the right half, where the density function is smaller, or is taller. I mean to say, not smaller, but taller. And so the random variable is less likely to show up on the left half than it is to show up on the right half. And that helps to convince us that the expected value of this random variable should be on the right half of the interval. Not necessarily seeing the 2/3 value explicitly unless we actually calculate it like we did. But you could look at this density function and believe that the expected value should be on the right half here. Questions are welcome. Again, there's a lot of material going on here. We're thinking about expected value as a probabilistic average. We're thinking about probabilities in terms of integrals of density functions. So we're integrating a couple of, we are bringing together several different topics from the course in this. And there's a fair amount for our intuitions to feast upon. But don't be discouraged if it's not making so much sense. Feel free to bring questions. The last task that was set before us was to find the standard deviation associated with this random variable. So if you're ever finding standard deviation, you first find variance. Standard deviation is just the square root of variance, so we're going to find variance and then we'll square root it. We're also going to use our theorem for variance, which says that you can calculate the variance as as the expected value of the square minus the square of the expected value. So that is a formula for variance, and it is one that we are going to make use of. We already know the expected value. It was 2/3, so we know it's square, 4 over 9. We got to find this bit, the expected value of the square. To find the expected value of the square, we had that theorem that involved the expected value of h of big X. Here h is going to be big X squared. H of big X is going to be big X squared. So the expected value of the square is going to be given by integrating the square of little x against the density function across the whole of the real line. And I'm going to skip the steps that I told you could skip. So we could break this integral up into the integral from negative infinity to 0, 0 to 1, which is the only non-zero integral of this triad of integrals, and then the integral from 1 to infinity, which is also 0. So we know the density function is 0 to the left of 0, it's 0 to the right of 1, and so the integral across the whole real line is just going to be the integral from 0 to 1. Here is the form that the density function takes in that interval, and now we can simplify and integrate. So I'm coming up with 2x cubed dx. The x cubed is going to go to x to the 4th, and it would be over 4, but 2 over 4 is giving me 1/2 x to the 4th. We're going from 0 to 1, ignore the scribbles, and we get 1/2 for the expected value of the square of this random variable. So we got the variance. The variance is the expected value of the square, which we just calculated to be 1/2, minus the square of the expected value, which was found in part C to be 2/3. So 1/2 minus 4 over 9, find a common denominator, and I come up with 1 over 18 as the variance. Standard deviation is the square root of variance. If you left your answer as root of 1 over 18, I'd be happy. Here I'm writing the square root of the ratio as the ratio of the two square roots. And then I'm factoring out 18 as 9 times 2, and the square root of 9 is 3. So I can pull a 3 out and leave the 2 under the root. This is the expected distance from the mean for this random variable. If you were asked to find and then interpret standard deviation, you might say that this is how far from the mean you would reasonably expect the values of this random variable to present themselves. Alright, so calculating probabilities, first of all, also calculating expected values and variances for this new random variable that I presented you with, the first continuous random variable we've worked with explicitly. So let's have you folks do one of these. Here's a sample problem. I'm giving you a different random variable now. Here is our sample space, an interval of the real line, this time -1 to 1, and here's our probability density function. So it's going to take the form of 3/2 x squared for x between -1 and 1, and it is going to be 0 otherwise. This is our density function. And I am tasking you with these trials, I suppose. I don't want to say that I'm tasking you with tasks because that sounds dumb. But I am setting before you these tasks. I want you to draw the density function. I want you to show me that if you integrate the density function over the whole real line, you get 1. This was a property we discussed that should hold for density functions since they do represent likelihoods. This is exactly analogous to saying that all the probabilities or all the values of the probability mass function for discrete random variables should sum to 1. For continuous random variables, they should integrate to 1. So check that that's true. Double check that this actually works as it should. I want you to look at the graph that you drew in part A and try to guess what you think the expected value would be for this random variable. We talked a bit about that in the example that we just completed, so of course feel free to scroll back and have a look. But I want you to look at the density function and try to come up with your best guess for what expected value should be. And then actually compute it. So find for me the expected value and find the variance. Check your guess. So go ahead and pause the video if you like, look back at old notes, feel free to collaborate with others. I am leaving the class meeting rooms on Blackboard Collaborate Ultra open all the time, so that's a space that you can meet with your peers in to discuss these problems if you like. If you want to use whatever else you want to use, that's also fine. But yeah, give it some thought. Feel free to look stuff up on the internet, look back at your notes. You can let me know if you have questions. I'll be happy to answer them if you email them to me. Alright, we will reconvene at this point and solve this problem. So first things first, I'm drawing my density function. It looked like a constant multiple of the quadratic between -1 and 1, and this is what the quadratic looks like. So this multiplied by 3/2, it would actually be a little bit steeper than the conventional quadratic, just x squared. Would be coming down here, not quite as steep. But it's got that quadratic profile between -1 and 1, and it was 0 off of that interval. So it's 0 over here to the left of -1, it looks like the quadratic in there, and it's 0 off to the right of 1. That is the picture. We were also asked to verify that if you integrate this density function across the whole real line, you get 1. So I'm integrating across the whole real line. I am skipping a step where I could have written in here the integral from 0 to -1 and also the integral from 1 to infinity, but both of those will be 0 since the density function is 0 over both of those intervals. Instead, I'm just left with the integral over the region where the density function is non-zero, well, except at the origin, but over the region from -1 to 1. And our density function takes this form across that interval. So between -1 and 1, our density function looks like 3/2 x squared. I can pull the 3/2 across the integral. The antiderivative of x squared is 1/3 x cubed, and we're going from -1 to 1. These 3's will cancel, 3 and over a third, or the 3 times a third will cancel, and I'm left with 1/2 x cubed from -1 to 1, and we are going to get 1 out of that. In fact, it's going to be 1/2 minus -1/2 to give me 1. So it does work. It does work as a PDF. It at least satisfies this property that a PDF should satisfy, that they integrate to 1. The total probabilistic mass associated with any random variable should always be 1. Now we are to guess what the expected value would be. And I'm seeing a perfect symmetry here with relation to 0. If I go over here to the right and I pick a value and I say how likely is it that my random variable shows up near that value, the area under the curve gives me that likelihood. if I move the same distance off to the left, I'm seeing the same area under the curve. So this random variable is just as likely to show up on the left-hand side in a small region as it is to show up in the corresponding symmetric right-hand side region. So there's no sort of preference for the left, there's no preference for the right here in terms of this interval. It's just as likely to show up in each little subdivision of the right-hand side as it is to show up in each little subinterval of the left-hand side that is symmetric with respect to placement and also size. And so I'm guessing this thing balances at 0. Another way you can think about these, they're called density functions because they do work a lot like physical mass density. So if I had a bar here and the bar laid on the interval from -1 to 1, this function would be describing how dense is the bar at each point along its length. So the bar is super dense over here at the left. The density actually drops off to 0 in the middle, which is theoretically impossible, but let's pretend that that makes some sense. And then the density of the bar increases again to high values once you get out to the other end. Because of the symmetric placement of mass within this bar, the perfect pivot point for the bar would be right here at 0. So if this were a seesaw bench where super dense wood was used on the end and some cheap pine is used in the middle and we got more nice eastern hardwood out here on the right hand side, then that, what are they called? That seesaw bench would have pivot point directly in the middle as you would like. So that's my guess, and that's my reasoning behind the guess. Thinking about the density function, thinking about different values that are possible and how likely they are, seeing a symmetry, and deciding that I think that the probabilistic average is actually going to come right down the middle here. Let's compute it. So the expected value would be the integral of x times the density function across the whole real line. The density function is only non-zero between -1 and 1, so we end up with the integral from -1 to 1, and we've got x times that density function. I'm pulling the 3/2 out front, I'm collecting my powers of x to be x cubed, and I'm looking at x cubed dx. So taking an antiderivative here, we're going to pick up a factor of 1/4, leaving me with x over 8, 3 over 8, x to the 4th power. And still we're evaluating that between 1 and -1. Because we've got an even power polynomial, it's just going to smash the negative here, and we're going to get 1 minus 1 as we plug those limits of integration into the antiderivative, and the difference is 0. So our guess was correct. We also want the variance. To find the variance, which I've got the formula right here, we have to find the expected value of x squared. So looking at the expected value of x squared, again, the density function is only non-zero in this interval from -1 to 1, and it takes this form in that interval. We can simplify. Now we're ended up with an x to the 4th power integrand. When we actually integrate that, we're going to end up with a quintic, or a 5th power polynomial term. So we're looking at 3 over 10, x to the 5th. Another thing that's worth saying, this is a bit of an aside, but if you're rusty on the integration stuff, always differentiate. If you think you've taken an antiderivative, always differentiate and see if you get back where you started. Math is full of things that are easy to do one way and hard to do the other. Differentiating is easy, integrating is hard. If you think you have done the hard way successfully, go ahead and cheaply differentiate. It doesn't take much to check, and make sure that your derivative is equal to the original integrand. If I differentiate this, the 5 comes down, the 5 and the 10 cancel to leave me with 3 over 2. The power drops by 1, giving me 3 over 2 x to the 4th, which is exactly my integrand here on the left. So I've done it correctly. And now I can plug in 1 and -1. With an odd power polynomial, we're going to have 1 minus -1, giving me 2 times 3 over 10, which is 6 over 10, which is 3 over 5. So that is the expected value of the square. Now the variance is the expected value of the square minus the square of the expected value. And that is going to be the 3 over 5 minus the expected value we found was 0. We square that, and we're left with just 3 out of 5 here for the variance. All right. We will next time in part 2 of this lecture. I actually have to check the timing and see how much time we have left in this lecture. I don't know how long we just ran. But certainly the next topic that we discuss is going to be normal random variables. We would have talked about some other famous classes of continuous random variables. In particular, we would have talked about what's called the uniform random variable. When we talked about discrete random variables, we talked about the discrete uniform. Here within the realm of continuous random variables, we could talk about what should be called the continuous uniform so that the notation would be symmetric, but it's actually just called the uniform random variable. We're cutting some topics that are sort of just an aside almost, that are not core material, so that we can do justice to the actual core material that folks are going to need getting out of here, some of the important statistical concepts that are going to come up later. So in the interest of giving you folks a fair shot at actually getting a handle on the important stuff here, we're going to pare down the course a little bit so that we have enough time remaining in the course to think about the big picture stuff. And certainly one of the big picture topics that still remains is the normal random variable, the most important random variable study in this course, arguably the most important random variable that humans have discovered, and probably if there were a bigger one we would have found it by now. So it's going to be core to everything else that we do in statistics as we move into the statistics third or so of this course. So we'll begin that next time. It is a continuous random variable, and we have laid some groundwork and some framework for being able to think about that random variable starting next time. So thank you, folks. I will see you again, or rather, maybe you will hear me again. All right, be safe and be well.